Okay, so we are talking about diagonalizable of a matrix. So, we just in the last class we defined the similar how to define the relation similar between two matrices. Just to recap, we have two matrices of size m cross n, n cross n. We say these two matrices are similar if one is written as some P inverse A P, where P is a non-singular matrix. P is a non-singular matrix. Then we say A is similar to B. Now, now we define the diagonalizability of a matrix. So, a matrix is diagonalizable if it is similar to a diagonal matrix D. Diagonal matrix or diagonal entries are there. So, say they are D1, D2, Dn. So, that means D is this matrix D1, D2, all diagonal elements are there, off diagonal elements must be 0. Or this di's may be, some of the di's may be 0, they are coming from the field element. Okay. So, if A is similar to a diagonal matrix, then it is called a then A is said to be diagonalizable. Now, in fact, if A is diagonalizable, then A and so A is similar to the diagonal matrix, that means A and D has the same eigenvalues. Now, what are the eigenvalues of D? Eigenvalues of the diagonal matrix are the diagonal elements. So, the eigenvalues of D's are this one D1, D2, Dn. So, they are the basically the eigenvalues of A. So, that means, if A is diagonalizable, then the A is, because they have the D and A have the same eigenvalue, this we have seen in the last class. So, that means, the A is diagonalizable to a this matrix, where we have the eigenvalues over here in the diagonal element. Okay. Provided A is diagonalizable, then it is the diagonal element will be the eigenvalues, because it will be similar to a diagonal matrix. Now, for the diagonal and these two matrices have the same eigenvalue. Now, we know for the diagonal matrix the eigenvalues are basically the elements, because if we have a diagonal matrix, what is the characteristics equation? Characteristics equation is nothing but D1 determinant of D1 minus x, D2 minus all are zeros like this, Dn minus x. So, this is 0. So, this will give us D1x, D2x, Dnx equal to 0. So, that means eigenvalues are nothing but D1, D2, so on, lambda 2, D2 like this. So, these are nothing but the eigenvalues of A, because they have the same eigenvalues. So, if A is diagonalizable, then it will be similar to the diagonal matrix, where the diagonal elements are the eigenvalues. Okay. So, if A is diagonalizable, then A will be similar to the diagonal matrix lambda 1, lambda 2, lambda n, all other elements are 0. So, this is the diagonal matrix of this, and this lambda i's are the eigenvalues of A. Provided A is diagonalizable, then A will be similar to this. Okay. So, that means, yeah. So, now we will have some properties, I mean necessary and sufficient conditions to be a matrix will be diagonalizable. So, this is a necessary and sufficient condition to be a matrix a diagonalizable. A is a matrix over a field over F is diagonalizable if and only if, this is the necessary and sufficient condition, if and only if there exists n eigenvector of A which are linearly independent. There exist n eigenvectors of A that are linearly independent. So, this is this condition is the necessary and sufficient condition. So, if it is diagonalizable, then we have n set of linearly independent vectors, eigenvectors, or the sufficient condition is if there are n set of linearly independent vectors, then it is diagonalizable. Okay, this is one theorem. We will see an example on this. So, if we cannot find the n set of linearly independent vector, then it is not a diagonalizable matrix. Okay, another theorem is telling. So, A is a matrix over a field, then it is diagonalizable if this is a sufficient condition, if the eigenvalues of A are all distinct. This is not the necessary conditions, this is sufficient condition. If eigenvalues of A are all distinct and belongs to F, belongs to the field F. Okay, this is another sufficient, because if this is true, if we have this, that means we know if we have eigenvalues are distinct, say lambda 1, there are n eigenvalues, they are distinct, then the corresponding eigenvectors lambda 2, then we have seen this result, corresponding eigenvectors, these are linearly independent set, linearly independent set of vector. Now, once we get linearly independent set of vector, that means this implies A is diagonalizable. Okay. Now, if they are distinct, then we have this result we have seen earlier. So, if we have distinct eigenvalues and the corresponding eigenvectors are linearly independent, then they are diagonalizable. Okay. So, this is another property, this is another sufficient conditions, and there is another condition which is also necessary sufficient condition for the diagonalizable of the matrix A. This is also if and only if. So, so A is diagonalizable if and only if, this is necessary and sufficient condition, if and only if all its eigenvalues are regular. All its eigenvalues are regular. So, what do we mean by regular? We know the definition of regular. Suppose suppose A is a matrix. So, it has eigenvalues say lambda 1, say there are k eigenvalues lambda 2, lambda k. Okay. They are distinct eigenvalues. Now, regular means if you take eigenvalue lambda I, so it has a geometric multiplicity, algebraic multiplicity. suppose is algebraic multiplicity is, so for every for all eigenvalues algebraic multiplicity must be same as geometric multiplicity. Algebraic multiplicity must be equal to geometric multiplicity. So, we know the algebraic multiplicity. Algebraic multiplicity means how many times it is coming in the root of the characteristics equations, and geometric multiplicity is if we consider the vector space for these eigenvalues, I mean eigenvectors that will form a vector space with the null vector and the dimension of that. So, that means number of linearly independent vector in that set. So, if the number of linearly independent of that set is same as the algebraic multiplicity of that, then that means if we combine all the eigenvalues, we have n such linearly independent eigenvectors. For example, suppose we have how to prove this? Yeah. So, suppose we have say this is true for all algebraic multiplicity, regular means algebraic multiplicity and geometric multiplicity are same. Suppose we have these are the distinct eigenvalues of A and their algebraic multiplicity say R 1, R 2, R k. So, that means lambda 1 is coming R 1 time in the characteristics equation, I mean root of this characteristic equation, lambda 2 is coming R 2 times like this. So, that means total root is n, R 1 plus R 2 plus R k is equal to n. These are the algebraic multiplicity. Now, we have the regular means the geometric multiplicity is also same. So, that means the eigenvector space of corresponding to lambda 1, it has dimension R 1. So, that means it has R 1 independent vectors. So, R 1 independent vectors. So, this is x corresponding to lambda 1. So, x lambda 1 1 x lambda 1 x lambda 1 R 1 like this. So, these are independent. Similarly, for these are independent. So, eventually we have all are n, eventually we have n linearly independent set of eigenvectors. Once we have that, then we know the earlier theorem, necessary and sufficient condition, that this is diagonalizable. So, this is another way to look at it. So, let us take an example. Let us take an example of a matrix A and we will see whether this is diagonalizable or not. So, you have to find the matrix P. So, again how to get the matrix P, that is important. Okay, suppose we have a matrix like this 3 2 1 2 3 1 0 0 1. Okay, now we are going to check whether this matrix is diagonalizable or not. So, that means we need to find out the P such that it will be if we multiply P transpose P inverse both sides, it should give us the diagonal matrix, and the diagonal elements nothing but the eigenvalues. So, basically first we need to find the eigenvalues of this. So, to find the eigenvalues we need to consider the characteristics equation of this matrix. So, this is 3 minus x 2 1 2 3 minus x 1 0 0 1 minus x. This is the characteristics equation of this matrix. Now, if you simplify this, we will get 3 minus x into this. So, this will be 3 minus x times 1 minus x, this is 0, then minus 2 of this. So, anyway, so you can do this calculation, eventually we will be getting, I have the calculator, but you can work out by your own, 1 minus x into this will be there in the note. x minus 1 equal to 0. So, this will be giving us x equal to 1 1 5. So, we have these are the eigenvalues. So, we have two distinct eigenvalues 1 and 5, and they are all coming from the same field R. Here underlined field is the real number. So, 1 is the algebraic multiplicity is 2 and 5 is the algebraic multiplicity is 1, 5 is coming 1. So, now we have to find their geometric multiplicity. If the geometric multiplicity, if they are regular, so that means if the geometric multiplicity of 5 is 1, because geometric multiplicity has to be greater than 1. So, for 5 we have no issue, that we have a eigenvector. Now, consider this we have to check with the 1. If for 1 we need to have a geometric multiplicity also 2. It must be less than 2, because geometric multiplicity is less than equal to algebraic multiplicity. So, we have to find the eigenvector corresponding to 1. So, let us try that, and if we can get two distinct eigenvector corresponding to 1, then we are done. So, let us try to get the eigenvectors corresponding to the eigenvalue lambda is equal to 1. So, how to get that? So, for that we need to solve this equation a minus. So, that is basically a x equal to lambda x. So, lambda is 1. So, if we take this side, so it will be giving us. So, 3 minus lambda is 1, 1, 2, 1, then 2, 3 minus 1, 1, 0, 0, then 1 minus 1, and x is x 1, x 2, x 3, this is 0, 0, 0. This is our x. Now, if we solve this, we will be getting like 2 x 1, 2 x 1 plus 2 x 2 plus x 3 equal to 0, and then we have only two equations, because this is becoming 0. 2 x 1 plus 2 x 2 plus x 3 equal to 0. So, we have these two are same, redundant. So, that means the solutions are coming as, we keep this. So, the solutions are coming in x equal to x 1, x 2, x 3. So, if we choose to be two variable, we have to choose x 1 is c, x 2 we are choosing d, then x 3 is decided by these equations. So, x 3 is minus 2 c minus 2 d. So, this is becoming like c d minus 2 c minus 2 d. So, that means it has two dimensions. So, c into 1 0 minus 2 plus d into 0 1 minus 2. So, these two are the linearly independent vector, like 1 0 minus 2 0 1 minus 2. So, linear span of this is the set of eigenvectors for this eigenvalue. So, this is the algebraic multiplicity, these are linearly independent. So, geometric multiplicity of this is 2. Okay. So, these two are linearly independent set of vectors. So, this is 2. Now, we have to get another vector which is corresponding to the 5, and we know that they are distinct. So, lambda 1 is 1 and lambda 2 is 5. So, they are distinct, definitely the eigenvector, these two will be independent with the eigenvector corresponding to 5. So, just we need to get an eigenvector corresponding to 5. So, these are the, so we keep it here. So, for lambda is equal to 1, we are getting this eigenvector 1 0 minus 2 0 1 minus 2. Now, we need to find the eigenvector corresponding to another eigenvalue which is 5. So, how to get that? So, lambda 2 is 5. So, for that we need to solve this equation 3 minus 5 2 1 2 3 minus 5 1 0 0 1 minus 5 x 1 x 2 x 3, this is 0 0 0. Okay. So, if you solve these equations, we will be getting like we will be getting x 1 x 2 x 3 as C 0. So, that means this or k 0, k is the another constant. So, k we take common. So, 1 1 0. So, this geometric multiplicity of this has to be 1. So, that is the vector which is generating the eigen vector space. So, then for lambda 2 which is 5, we are getting this eigenvector 1 1 0, and if we check, if we take any two vector, if you take a vector from here and here, they will be independent, because they are coming from two distinct eigenvalues, and we know the result. If you have two distinct eigenvalues, their eigenvectors must be independent. So, these are the set of independent eigenvalues. So, vectors. So, we have 3 independent eigenvectors. So, that means this A must be diagonalizable. So, this implies A is diagonalizable. So, we have 3 set of. So, this is 1 0 minus 2 0 1 minus 2. So, we have 3 set of linearly independent eigenvectors. So, this implies A is diagonalizable. Okay. So, A is diagonalizable. So, now how to get that P? If A is diagonalizable, then it must be similar to the diagonal matrix where the eigenvalues are residing. So, for that, if you multiply P inverse A P, then we must get this diagonal element. So, P are nothing but this matrix. So, the P will be this independent matrix. So, this we can write this here. So, if you construct this P to be, we just take the column of this 1 0 minus 2 0 1 minus 2 1 1 0. If you consider this to be P, then we can easily verify that if you multiply this P inverse A P, then it will be similar to a diagonal matrix, and that diagonal matrix will be the diagonal element will be the eigenvalues. So, this will be the, what are the eigenvalues? 1 and 5. So, 1 1. So, this 1 1 will corresponding to this 2 row and 5, and all the elements will be zeros, other elements. Okay. So, this P we can get from this, we can easily verify this. If we just take this P and that A, you multiply this, and then again you multiply with the P inverse of this, you have to find the inverse of this, then we will get the this diagonal matrix, where this is lambda 1, where the eigenvalues are sitting there. Okay. So, that is the result. So, if it is diagonalizable, then we have a P. P is nothing but the diagonal elements which are becoming this. Okay. Now, if the so we take another example where eigenvalues are not regular. In that case, it is not diagonalizable. So, that example, we can take a quick example. Yeah, we take another example. So, suppose we consider this matrix A, which is again 3 by 3 matrix 1 1 3 1 1 4 3 1 0 0 1. Okay. We want to check whether this is diagonalizable or not. So, for that we have to find the first the eigenvalues of this. So, to find the eigenvalues we need to take the characteristics equation 1 1 4 3 minus x 1 0 0 1 minus x equal to 0. So, this will give us the 3 minus 1 0 0. If you say solve this, it will be x is 1 1 5. So, the eigenvalues are same as the earlier matrix, but the problem is here we will try to find the. So, this is lambda 1, this is lambda 2. We have two distinct eigenvalues, lambda 1 and lambda 2. Lambda 1 is 1, whose algebraic multiplicity is 2, and lambda 2 is 5. Now, we just need to check the geometric multiplicity of this lambda 1. So, if it is not 2, then this A matrix is not diagonalizable. So, for that we need to find the eigenvector corresponding to lambda 1. So, for that we need to solve this equation 1 1 4 3 minus 1 1 0 0 1 minus 1 x 1 x 2 x 3. This is 0 0 0. So, if you solve this equation, we will be getting this x to be x 1 x 2 x 3. This is nothing but some c into 1 minus 2 0. So, this is bad luck. So, this is basically the dimension of this vector space, I mean eigen space corresponding to this eigenvalue is 1. So, we have only one independent vector. So, that means, this is the geometric multiplicity of this is multiplicity is 1, which is not same as the algebraic multiplicity. So, that means, we cannot get two independent vector where we can construct the P. So, this implies A is not diagonalizable. So, we cannot get a P for which this is happening. So, you can have more example. So, in the node we will be giving some more example to work out. Thank you very much.